Hey everyone, welcome back. This is the second lecture in the video series for Chemistry 227 here at the Pennsylvania State University, at least how I teach this course. It's the second lecture or second video on spectroscopy. So we're going to pick up where we left off last time on the PowerPoint slide. So I'm just going to share my screen here. Get busy. Okay, let me see if I can hide these meeting controls here. Myself right there. Okay, so we left off with some demonstrations and some interesting information. So a lot of the information I presented the last time is not necessarily stuff that I test on or we have exams on. It's just some background information, something for students to think about, that there's a bigger picture out there with respect to electromagnetic radiation, how we use it to probe chemical systems and things to think about, etc. So, of course, we discuss what is and what isn't on exams, what they should know. They should know, really try to retain all that information if at all possible, because it's useful. But anyway, let's move on. So, we've been talking about everything except absorption of radiation by a chemical system. And before it was just diffraction, reflection, refraction, scattering. But what we're really interested in here, at least for this course, and in a lot of applications, is the absorption of radiation and the changes or transitions that induces within chemical systems. So this is just what would be known as a Jablonski diagram, because there's so many different molecules are fairly complex, etc. And typical Morse diagrams really express the changes that are taking place with respect to one reaction coordinate, which is great for a diatomic molecule. But as we get into more larger, more complicated molecules, we just look like at an overall electronic or overall vibrational state of that particular molecular species. And so that's what this is. And so the S0 ground state here would be essentially the ground electronic state associated with a given molecule. And then superimposed on that are these fine blue lines right here where the spacing gets essentially closer and closer. Those are vibrational levels that are superimposed upon the overall S0 ground electronic state. Okay, so ground S0 is the ground state of that for that molecule. And then we have superimposed on there different vibrational states that can exist within that molecule. Okay. And then we have two singlet excited states, so S2 and S1, and these are associated with different transitions, an electron from one orbital, ground state orbital, to an anti-bonding orbital. And so we'll get into that a little bit here, but we can have an absorption of a photon taken to any S1, S2, maybe S3, S4, etc. There could be a number of different singlet excited states depending on the molecule. And it can be excited up into any one of the excited vibrational states within each of those excited electronic states, just depending on the energy of the photon and the energy being absorbed. Okay. Well, one thing we don't show in this is the T1, which is known as a triplet state, where there's a change in the spin orientation of the electron that's being promoted to a higher energy orbital. These, from a quantum mechanics, these types of transitions are not permitted or allowed. They do occur, but quantum mechanics essentially says that they can't, because it's anyway, but molecules can reach the T1 excited state through all three means other than direct absorption. Anyway, so a couple things can happen right here. So the excited state would be going from essentially ground state orbital to an excited state orbital configuration, and that would be a S2, S1, or T1. Okay, so if we look at the far left over here, the subsequent slides are going to delve into this a little bit more detail, but I'm probably going to skip over them a little bit. But if I have the absorption of a photon going from the ground vibrational state and the ground electronic state, so the thick line at the very bottom right there, as most molecules at room temperature in their ground vibrational state, absorption of photon promotes it to a higher vibrational state. within the S2 excited state. And so what happens almost immediately is essentially vibrational relaxation down to the ground vibrational state within S2. That occurs at a fairly rapid time scale. And I'm not sure if I have time scales on I know I have them here on subsequent slides, but essentially the absorption is a fairly quick phenomenon. It's almost instantaneous. 10 to the minus 15 to the minus 14 second time scale. And then vibrational relaxation essentially occurs on a slower time scale, several orders of magnitude slower. And so there's essentially during absorption, there's really no translation or vibration associated with that absorption event because it happens on such a quick time scale that essentially nuclear coordinates don't change on that time scale. Anyway, but we get rapid, following the absorption, we do get vibrational relaxation following that. Okay, and then a couple of things can happen. It can find essentially through intersystem crossing a high vibrational state, right? A higher vibrational state associated with the S1 excited state, which is a different electronic excited state. But the lowest vibrational state of S2 probably has a comparable energy level associated with a higher vibrational state in S1. And so we get this intersystem crossing. And then the same thing can happen from S1 to S0, which I don't show here, but that can happen as well. And actually that's going to happen more times than anything else because vibrational relaxation happens on a fairly quick basis. And so intersystem crossing can be quite rapid and lead to the de-excitation back to the ground vibrational state of the ground electronic state fairly rapidly after the absorption of a photon. And that's primarily what happens. There are certain conditions where something else might happen, such as fluorescence and phosphorescence. Again, we can get promotion of an electron to the S1 excited state, a highly vibrational state within that, where we get vibrational relaxation down to the ground vibrational state. And as I said, in either case, we can, usually we get essentially, we find a radiationless transfer is the most efficient means where the S1 state now finds a high vibrational state within the S0 ground state, undergoes intersystem crossing, and then just relaxes itself all the way back down. It's called radiationless transfer and happens essentially the majority of the time. Okay. Now, we can find ourselves with molecules that essentially are locked in this S1 excited state. And these molecules tend to be highly conjugated. They tend to be fairly planar. They have very little interaction with the solvent. So they really don't, there's not a lot of interaction between the molecule and the solvent. So they tend to be stiff, planar molecules, highly conjugated, and they tend to what's called fluoresce. And that's what that emission is. So that emission in black and then that time scale, 10 to the minus 10, 10 to the minus 7 seconds, results in the emission of a photon. So since there's little chance of the molecule to vibrate itself down to the ground electronic state, the ground vibration state, the ground electronic state with minimal interaction with the solvent, it can be locked in that position long enough to essentially give off a photon. And this is called fluorescence. So the emission of a photon, then it's called fluorescence. And what we can see here is that the fluorescence will always occur at a wavelength equal to or longer than the absorption photon, the photon that was absorbed in this event. And we'll see that in a couple of other slides. In some cases, it can undergo an intersystem crossing. So instead of internal conversion, IC, it can undergo internal system crossing to the T1 excited state. And this is where the electron flips its spin state as well. And so once we get that intersystem crossing, it can wiggle itself down to the ground vibrational state of the T1 state. And from there, again, it's usually more efficient to essentially wiggle itself down to find a comparable high energy, high vibrational energy state in S0 and then wiggle itself down. But in some cases, it can be locked into that ground T1 state, the ground vibration state of T1, long enough for it to emit a photon to relax back down to the ground state. And that occurs over a very long time interval, but we call that phosphorescence. Now, when it comes to these transitions, the energy necessary to induce an electronic transition, so S0 to S1 or S2, is typically on the order of 10 times the amount of energy necessary to induce a vibration. So in S0, Raman and IR are essentially, we're trying to induce transitions between those lighter or thinner lines in the S0 representing different vibrational states. And so those take much less energy to induce a vibration within a given molecule as when it remains in the same electronic state. And then I don't show the rotational states here, but superimposed on those vibrational states in each of these excited states are rotational states as well. And those are approximately a factor of 10 smaller than the energy necessary to induce a vibrational state as well. Okay. So what absorbs? What types of electrons absorb? So the electrons that absorb are typically the electrons that are valence electrons involved in bonding. Okay, so these are pi electrons, sigma electrons, and even lone pair electrons. And DNF electrons, as you learned from crystal field theory and general chemistry as well, and then also associated with charge transfer. So electrons that contribute to absorption by organic molecules are essentially those that participate directly in bond formation, and then also non-bonding, highly localized lone pair electrons about oxygen, nitrogen, sulfur, and halogens. So if I have a single bond, right, these are described by sigma orbitals or electrons in sigma orbitals or in the sigma bonds, and the electron density here is symmetric about the bond axis. If I'm looking at double bonds, well, they have both pi orbitals and sigma orbitals, and pi orbitals have low energy density along the bond axis, but they have maximum electron density above and below that axis. And so these are the ones we're typically looking at in addition to the non-bonding. Okay, so just some examples here. If I go from a sigma to a sigma star, so the bonding to anti-bonding orbital, or the sigma to pi star transitions, these typically require a huge amount of energy and put us into what's called the vacuum UV. And typically you're not going to observe these in most instruments, in most research labs, or especially instructional labs. And so these transitions are inaccessible for the most part for standard routine research grade and instructional grade instrumentation. The N to sigma star and pi to sigma star transitions, these involve one non-bonding electrons or lone pairs, typically in the wavelength range 150 to 250. So some of these we will see or are able to see. Most instruments will go down to about 190 nanometers. And so that's typically the lowest wavelength working range or lowest wavelength limit of most spectrometers. And then we have the N to pi star and pi to pi star transitions, which you're probably most familiar with if you've been in organic and gen chem, et cetera. So most common transitions observed in organic molecular UV vis, observed in compounds with lone pairs and multiple bonds with lambda max in the 200 to 600 nanometer region. If we just look at examples right here, so CH bonds 125 nanometer to get a sigma to sigma star transition, CC 135 nanometers. These transitions in water and methanol, typically for these N to sigma star and pi to sigma star transitions, epsilon is small. We'll define epsilon later, but typically what it means is that the probability is fairly low, and so the intensity of these peaks is fairly low. And then for 3A, epsilon is typically small for the N to pi star transitions, so these tend to be weaker peaks and fairly large for the pi to pi star transitions. If I look at formaldehyde, so this would be if I can look at all these transitions with formaldehyde, so I can see the sigma to sigma star around 125 nanometers, the N to sigma star, pi to pi star, N to pi star. That's a forbidden transition because that's a triplet transition, S0 to T1. But theoretically, we can't observe it. Selection rules essentially forbid against that, but in reality, nature does what it wants, and we can see that transition. It's difficult, but you can see it. Just an example right here. So these are relative energies of the ground and excited state orbitals and the transitions for a hypothetical functional group CCO. And essentially the different transitions right here. So S0 to S4 is a sigma to sigma star transition within this molecule. The S0 to S1 is an N to pi star transition. And just kind of to show you the orbitals and antibonding orbital relationships and the transitions between these for this hypothetical molecule. Okay, so what we want to use is essentially absorption of the photon to tell us something about that molecule. In this case, is, if it's there, how much is it there? And so most of our absorption spectrophotometers, anything that uses absorption, like FTIR, UV vis, we're using what's called a 180-degree instrument design, where essentially the sample, the light source, the sample, and the light detector. So the source, the sample compartment, and detector are arranged along a line, a 180-degree line. So the geometry is 180. As we'll see for fluorescence, we're going to actually bend this. So essentially what it means is that when I set this up, the blank is, I'm going to put in my cuvette holder, essentially a blank that contains the solvent, everything but the analyte or analytes of interest, so that I can measure the amount of light that strikes that detector in the absence of any absorption taking place. Now, there might be some scattering and some bending of the light due to refractive index changes and stuff like that between materials, rough surfaces. So essentially, I use the blank to kind of capture what would be there hitting that detector in the absence of just the analyte itself. Then I'm going to put essentially my analyte in there, my sample, and I should have the exact same conditions. Same cuvette, same solvent. The only thing different should be the presence of my analyte. And so when absorption occurs, then less light is going to hit that detector. And we call that P. And so essentially what we're going to be measuring is the transmittance. The transmittance is the ratio, the amount of light that hit the detector in the presence of a sample relative to that which hit the detector in the absence of the sample or in the presence of the blank. And if I multiply that by 100, I get percent transmittance. All right, so here's just a cartoon. Essentially, I'm looking at essentially a total, a number of photons, I think maybe 100 total, and looking at how many photons are captured. And when I mean captured, this would be absorbed, okay, by the analyte. Captured may not be the best terminology here, but I'm looking at essentially a system that contains, sending in 100 photons through my cuvette. How many are absorbed versus how many make it through and hit the detector, okay? And so as the concentration increases from 1 to 50, no particular units here, I can see that the number of photons absorbed by the sample increases, right? More analyte molecules, chance of a greater chance that absorption is going to take place, or that a photon's not going to make it through. And so I can plot photons captured versus the concentration, or I can say photons registered by the detector, those that made it through and hit the detector as a function of concentration. And what we can see is that these are non-linear, right? Non-linear. And so if I do a ratio, P over to P0, right? So P0, right, would be 100. Presumably all of them hit the detector in the absence of the sample, and then fewer and fewer hit the detector as the concentration increased. This is what I get. It's a nonlinear curve. And so transmittance here, which is the ratio P over P0, is not linear with respect to concentration. So one, there's no linear range of response, and so we can't use this relationship, okay? And so we want to transform it. And there's another thing that we don't like about this, right? As I increase the x-axis, we usually like to see a change that increases with respect to the response, right? It's just natural. As human beings, we like to see positive relationships here, right? Positive slopes. And so what I want to do is find a way to take this data and make it linear with respect to concentration, but also increase so that the response, whatever I have, increases with concentration. And so what I'm going to do is I'm going to take the log of that, okay? So I'm going to take the log of that ratio, and that's what's plotted on the left-hand curve right here. And the log of a number less than 1, because remember, P is always smaller than P0, is a negative. And we can see, okay, well, as concentration increases, right, I have a linear relationship now, okay? As maybe I didn't notice before, but when I see this P over P0 versus concentration, that curve immediately suggests to me there's a log dependence, okay? And so I'm going to take the log of that. And so what I've found is that now I have a straight line relationship, right? There's a linear relationship between the log of that ratio and concentration. The only problem is that it has a negative slope. And as I said, I'd like my signal to increase. So all I'm going to do is take the minus of that of the log of that ratio. And when I do that, I essentially get a linear line relating essentially absorbance. When I minus log P over P0, I'm going to call absorbance relative to concentration. And so these are the Beer's law plots that we typically make, right? Where concentration is the independent variable. It's what I change, and then see what the response is in my instrument to that change in that variable. And that's the y-axis. The absorbance is the response to that change in concentration. And so I see a nice linear relationship that is has a direct dependence, right? Direct relationship one on the other. So as one increases, so does the other one. And it tells me, since there's a linear range response, that absorption is directly proportional to concentration. Awesome. So if it's directly proportional to concentration, that's great. But I also know that if I increase the path length, light has to travel through more of that material. More photons on average are going to get absorbed. Okay, so I know that absorbance is going to increase with path length. Okay, so I know that absorbance is proportional to both path length and concentration. Okay, and this is kind of the same format for PV equals nRT, right? In terms of building up the relationship between pressure and volume and number of moles and temperature of the gas, etc. All right, so what I'm going to use is, I know that absorbance is proportional to these, so I'm going to introduce a constant of proportionality, so I can make an equal sign. And so that's what the epsilon is. And the epsilon is the constant proportionality relating absorbance to the path length and the concentration of the analyte. Okay, and we know that absorbance is equal to epsilon BC then, and epsilon BC is equal to minus log of the transmittance. Great. Now, epsilon is more than just a constant of proportionality, though. Okay, there's actually some significance to this number, because it's a characteristic of the molecule of interest. Each molecule has a different epsilon associated with it, and it is a characteristic fundamental property of this particular molecule that is tweaked by the solvent that the molecule is in. Now, Beer's law holds for a number of things, right? One, we need to be operating the linear range of response, okay? And to ensure that, one, when we specify this, we need to specify monochromatic radiation. And we're going to see why in just a second, because epsilon is a function of wavelength. But also, the more light that comes in, essentially the greater the deviation from Beer's law. We're not going to get into that, something we get into at the higher level. But we also want molecules to behave independently and identically with respect to each other. So all the same molecule needs to behave identically and independently of each other. So they must be independent absorption centers that behave identically to each other. And so dilute solutions are necessary, because as we increase the concentration of the analyte, analytes begin to behave a little bit differently. And so, so these are critical. Okay. So this is just a plot, and this is taken from the Harris book, that's showing that epsilon, okay, is wavelength dependent. So we can see that at different wavelengths, epsilon is different. And the reason why this is then is that whenever we do absorption studies, and we want to be quantitative using Beer's law here, I think I have it right here, we have to specify a wavelength, right? Because epsilon changes. Concentration doesn't change as a function of wavelength. That's just what I have, whatever I make the solution to be, or whatever the analyte concentration is in the solution. B, the path length, is independent of wavelength, okay? But epsilon is dependent upon wavelength. We'll see that in the next slide. So that means absorption is independent of wavelength. If epsilon was independent of wavelength, then our absorption profiles would be just flat lines. There would be no definition to them, right? Because B doesn't change as a function of wavelength, C doesn't, and if epsilon didn't, we would just have a horizontal line as a function of wavelength, absorbance versus wavelength. And we don't see that. We know that in absorption profiles, molecules have essentially absorbance that changes as a function of wavelength, and that's because of epsilon. And the reason for that has to do with something known as the Frank-Condon principle. So these are called Morse diagrams here, looking at a specific reaction coordinate. But what it says is that and the lower E0, which would be my S0 in my prior diagram. This is a Morse potential, essentially showing essentially the energy between two nuclear coordinates in a chemical system, and as they move away from each other, okay? And so where that V double prime equals 0 at that lower graph right there, E0, that's the lowest vibrational state in the S0 ground state, okay? And so absorption of a photon is instantaneous, so there's no change in nuclear coordinates. So that arrow, that blue arrow, goes straight up, right? There's no translation of the nuclear coordinates because absorption occurs on the time scale of like 10 to the minus 15 seconds, whereas vibration is like 10 to the minus 12 seconds, right? It's much slower. And so the most likely transition to occur between S0 and S1, or E0 and E1 in this diagram, is where essentially the wave function, the electronic wave function, are in phase. So the electronic wave function in E0 at that ground state finds essentially a wave function that's in phase in S1. And that blue arrow is pointing to the only vibrational wave function that is directly in phase. They're both at their maximum in this particular diagram. And so that transition is the one that is most likely to occur. Okay, and so we can see here for in the blue at the very bottom diagram, you can see that for the absorption there, that 0 to 2, that's essentially going from V equals 0 and E0 to V equals 2 and E1. That is the largest peak right there, right? Because it is the most probable transition to happen because those two wave functions are in phase with respect to each other. The more they are out of phase, the less likely that that transition is going to happen. And so this is why epsilons are dependent upon wavelength, because they're dependent on the probability of essentially V equals 0 and E0 going to V equals 0, 1, 2, 3, 4, 5, 6 in E1. And it has to do with how close they're in phase with each, the vibrational wave functions are in phase with each other. And so that's why it changes as a function of wavelength, okay? So without that, we would just have straight horizontal absorption profiles in our spectra of essentially absorption versus wavelength. So it's this wavelength dependence of epsilon, okay? Great. Okay, so this is getting into essentially step-by-step what can happen for this one. I talked about it before, so I'm just going to move through it here and not talk in great detail about this, but you can take a quick picture of this and move on. Or stop the video, et cetera, to read it. But it's essentially talking about absorption of a photon and what can happen as we go up, okay? All right, so when it comes then to emission, so we get into a state here where we have a molecule where it's favorable for it to emit a photon to relax back down to the ground electronic state, okay, either through fluorescence or phosphorescence. In this case, we're mainly looking at fluorescence here. Okay, so a couple things can happen. So on the left-hand side here, we have the absorption spectrum. So we're starting in the ground vibrational state of S0, because that's the lowest energetic state in the ground electronic state. And then absorbing photons of different wavelengths or different energies can promote that molecule to S1, any one of those vibrational states in S1. Okay, the higher energy being the lambda plus 5, right? Higher energy, smallest wavelength. Okay, all right, so if I look, now remember, once we get into the S1 electronic state, no matter what vibrational state we're in, vibrational relaxation occurs fairly rapidly. And so we're going to get immediate, essentially, relaxation down to the ground vibrational state in S1, okay? And it's going to stay there. If it can't find a high vibrational state in S0 to do an internal conversion and then wiggle itself down to the ground vibrational state in S0, it's going to emit a photon. And that's what it's showing here, lambda 0 to lambda minus 5. Lambda 0 for the emission has the same energy as lambda 0 of absorption, okay? But all other wavelengths that are being emitted by release of a photon to relax back down to any one of those vibrational states in S0 is a longer wavelength, lower energy photon than was absorbed. So the lambda of excitation is always smaller than the lambda of emission, or the energy of excitation is always greater than the energy of the photon being emitted. Okay, but what happens though is because these are very small changes. Promoting an electron from pi to pi star doesn't result in huge changes in the molecular configuration, and so the vibrational levels in S1 and the vibrational levels in S0 are nearly identical. Okay, and so the transitions then to these different vibrational levels, these different electronic states, really are very similar to each other. And what it says then is that the absorption and emission profiles are almost mirror images of each other. And that's what this is showing. The black line is absorption, the absorption profile for this molecule. And then the blue line is the emission profile for this particular molecule, right? And you can see they have very similar shapes. And the reason why is because the epsilons for absorption are the same, right? And you're also, when you're emitting a photon from the S1 down to any one of the vibrational levels in S0, right, the most favorable emission is going to be to that vibrational state that's in phase with the ground vibrational state in S1. So you get these mirror images here. And so if you were to plot both, this is what we would see. All right, a couple things. Absorption, as we already talked about, is essentially 180 degree spectrometer design, that the sample being the pivot point is 180, forms 180 degree angle between the source and the detector. Well, in emission, that's different, okay? And the reason why is that emission is actually a fairly weak phenomenon, right? So very few molecules, even if they are locked in that state, still quantum efficiency of fluorescence is really small. And so most molecules, well, I should say very few molecules are going to ever fluoresce, and even fewer phosphoresce. And so what happens is that if I have a 180 degree design, I'm going to have very small emission and a sea of radiation from the source. And remember, it's hard to see a very small effect when it's surrounded by a bunch of noise. And so what we want to do is remove that noise. And so in a 90 degree design, what happens is that any radiation not absorbed by the sample essentially just passes straight through that sample, right? But the radiation that's actually fluoresced, which fluoresces in all directions, the fraction that fluoresces at a 90 degree angle with respect to the radiant source will make it to the detector. So it essentially, in the absence of any analyte, that detector is completely dark. No light is hitting that detector because there's no sample emitting in that direction, right? So all this, there might be some small scattered radiation going in that direction, but essentially the radiant source, light travels in straight lines. And so it's going to go right through that sample and be absorbed by the walls of the spectrometer and won't make that right turn to the detector, essentially. So when we do emission studies, essentially the detector is at right angles to the radiant source and the sample is the pivot point. Okay, so a couple of things. Absorbance profiles have a particular shape right here. Remember, we have the linear range of response, which is that black curve. We also have that dynamic range, which the red curve represents both the linear and the dynamic range in total. But we can see something, that it begins to essentially level off and it will remain flat, okay? And that's because no matter what we do, right, no matter how concentrated the sample, no matter how much of the source radiation is absorbed, there will always be some light hitting that detector. There's no way to stop it. There's stray radiation coming from everywhere. And so there's always going to be some finite illumination of that detector surface, okay? And so P over P0 hits some constant value, which means that minus log P over P0 hits some constant value that we can't essentially get above. And so that's why they flatten out these absorbance profiles. Down below, what we can see here is that we have the far left cuvette has a low concentration. And so photons are being absorbed all throughout that cuvette volume. As I increase the concentration, more and more absorption is taking place at the front end of that cuvette, because even though the molecules are randomly distributed, there's just a lot of molecules. And so we see a lot of the light being absorbed early on. And at very high concentrations, effectively all the light is removed or absorbed and none of it makes it to the detector. But we have a flat line here because there's some stray light limit that we can't essentially go past. So there will always be some stray light hitting. In contrast, in fluorescence, we have a linear range of response, and then we're going to have a dynamic range, but we're going to have a different effect take place at the end of it. So this is so describing the linear relationship, very similar to Beer's law for fluorescence. We get into the bigger equation in the study guide and in the class when we work on problems. So the K is a constant right there. But this is what can happen with respect to fluorescence. Okay, and I do have my own data on this as well, which I should be using the figure for. But we can see there's a linear range response, a dynamic range, and then above, about 1.2 micrograms per mil, we see this bending over, right, of this curve. And so how can that happen? And so this is what we see. So this is my cartoon of this. So at low concentrations, the activation volume is the same. So absorption really kind of occurs throughout the cuvette volume. And then we get essentially, we're looking at emission now, right? So a molecule has to absorb the incident radiation, but then it's going to emit a photon of a longer wavelength. Okay, but it's emitting photons at many different directions. So only those that are emitted towards the detector are actually seen by the detector. Okay, and so that's great. So at low concentrations, we have a linear range, but then it starts tipping over a little bit. And the reason why it's tipping over a little bit is because one, it's going to curl back on itself. And that's because as the concentration gets bigger and bigger, absorption is mainly occurring at the front end of that cuvette, right? And so now the photons being emitted, where they're being emitted from is displaced from that 90-degree design with that detector. And so fewer photons can make it out and hit that detector because they're being emitted in a region of that cuvette where there's no path towards the detector. And so fewer photons hit that detector. Fewer photons hit that detector, we get a smaller signal. Okay, and so in fluorescence emission, we can see that it will curl back on itself. This is known as an inner filter effect. Because it's essentially filtering the photons from being able to leave that sample compartment and hit that detector, because all the absorption and emissions taking place at a very narrow region within that cuvette. Okay, great. I am trying to get out of this. Thank you. Okay, so that's the end of the first set of PowerPoints for spectroscopy. There's another set of PowerPoints that we'll go through that will essentially conclude the spectroscopy. Again, whenever we do anything like this in lecture, we're spending time working on problems. There weren't a lot of problems on this one, but there are on the next one. And we also have days where we do nothing but work on problems. And then, of course, once we've lectured on this stuff, we do work with the lab that we do, because the lab is tied to the lecture. So we have completed at least the main series of lectures before we start the experiment in lab. So that lab is intimately tied to the lecture. We've talked about it, discussed about it, worked on problems in the lecture, and then we go into the lab and actually do experiments involving those concepts in the mathematical calculations, etc. Okay, so next time we'll talk about applications. How do we use absorption spectroscopy to calculate concentrations, to calculate various properties of materials, looking at mixtures? Can I use spectroscopy to tease out the individual concentrations of components in a mixture? And if I can, that's great. But what are the limitations of that? Because at some point in time, maybe the spectra are too similar, or there's too many components and I can't do that, and I'm forced to go to chromatography to separate things out so I can probe them individually. So those are the applications we'll be discussing in the next lecture. All right, take care.